0 and 1, also known as binary values. Okay. So in this digital electronics, we'll be discussing about the digital circuits and logic gates. So the digital signal is the one which is either one high value or a low value. 1 stands for high value, or 0 stands for the low value. Okay. This 1 also stands for on or yes, whereas 0 represents off or no. Similarly, low, and this is high. Okay. So digital signal is either 0 or 1. 0, off, no, low, all these will take low voltage input. And the high value is 1, or it stands for on, yes, or high, which uses high voltage. Now, what is the digital circuit? The circuit which uses digital signals is known as a digital circuit. So digital signal is either 0 or 1. This is known as binary signal, binary values, which has only 0 and 1 in binary system, binary number system. Now coming to the logic gates, see, these are the actually building blocks which uses the logical relationship between input and the outputs. The digital circuit having a certain logical relationship between the input and the output voltages is known as a logic gate. Okay. So there will be a logical relationship between input and output. Now, truth table is the representation of all possible input combinations and the corresponding output values of that logic gate. This is truth table. So for every logic gate, there will be a truth table. Based on the number of inputs, you will get different combinations. In general, we will be dealing with 2 input logic gates. Now, there are 3 basic logic gates in this. They are OR gate, AND gate, and NOT gate. These 3 are the basic logic gates. And also, we'll have combinations here. NOT and OR, NOT plus OR. This combination gives you a new gate called NOR, NOT plus OR. Similarly, NOT plus AND. This gives you a NAND gate. We'll be learning about these gates also. So primarily we have OR, AND, and NOT gates in this. Okay. Now, what is an OR gate? Here the logic itself is OR. What is that logic in OR? I'll show you now. So it is a gate which has 2 or more inputs and 1 output. The output is high. High value is nothing but 1. Remember that. The output is high if 1 or more inputs are high. Either it can be 1 or more than 1. Suppose if you use 2 inputs A and B, it can be A or B that can be high to get high output. So that's what is OR logic. Understood? Now, symbolically it is represented like this. This is the symbolic representation of OR gate. OR gate. From now onwards, by looking at the gate, you need to realize what kind of gate it is. Okay. Now, the logic relation here is A plus B or A or B. To get a high output, either A or B has to be high. A or B. That's what is OR gate. Okay. Now, observe this circuit. This itself tells you what is OR logic. See, here is the battery. Current passes this way. The two switches are in open condition. It's an open circuit. Here is the bulb. If bulb glows, that is taken as 1. If bulb doesn't glow, that is taken as 0. High, low, glowing, non-glowing. Okay. Now, take these two switches as A and B. Two inputs, A and B. Now, analyze the circuit. What is the condition for this bulb to glow? Which switch has to be closed? See, when both are open, the bulb is not going to glow as there is no current passing through this path. Both are open means both are zeros. The output is also 0. Now, assume that A is closed. The first switch is closed here. When switch 1 is closed, I am talking about this switch. Then current can pass through this circuit. Current passes through the bulb. Bulb will glow. So only first one is closed. Second one is in open mode. But output is high. See, A is high, B is low. Output is high. I am taking these as A, B inputs and this is output Y. Now, keep this first switch open, A open, close B, means A remains 0, but B becomes 1. Even then, current can pass through this circuit and bulb will glow. You will get high output. What if both switches are closed? If both are closed, there is no problem, current will pass through the bulb. Both are closed means both will become 1. Output is 1. Now, this is what is called the truth table of OR gate. Truth table of OR gate. With the two inputs, A, B are the inputs. These are the possible combinations. For two inputs, there are 4 possible combinations: 0, 0, 0, 1, 1, 0 and 1, 1. Now see, high output is obtained when any one of the inputs or both the inputs are high. If both are low, then output is low. Otherwise, output is high when either A or B is high. So that's what is OR logic. Understood? This is OR gate truth table. Now, using the diodes, an OR gate can be constructed with the help of diodes like this. Two diodes, A and B are the inputs. When any one is high, then diode conducts and you will get output across this load. Okay, either D1 for A is high, D1 will be conducting. For B high, D2 will be conducting. When both are high, these two diodes will conduct and will get output across this. That is OR gate. And truth table, when both are zeros, only in that condition the output will become 0. When both are zeros, 0 or low input. When A and B both are low, output is low. Otherwise, it's high. Either A or B can be high to get high output. If both are high, that's fine. We'll get high output. Understood? A or B. That's what is OR gate. And here is most important observation from OR gate. For OR operation, A plus 0 is always A, irrespective of the value of A. See, here only two values are possible for A. A can be either low or high. Either it is 0 or 1. Now, A plus 0. If A is 0, 0 plus 0 is 0. And if A is 1, 1 plus 0 is 1. So, if this is A value, you are getting output also same thing. That's why A plus 0 is A. And A plus 1 is always 1 irrespective of the value of A, either low or high. In the same explanation, suppose if you use 1 here, 0 plus 1 is 1. 1 plus 1 is also 1. It's not 2. There is no number 2 in binary system. It's only 0 and 1, low and high. Now, see, for any value of A, the output is always 1. That's why A plus 1 is 1. A plus A is always equal to A. Remember these relations. Okay, so that is about OR gate. Now let's see the next one, AND gate. AND. Using the previous logic, what would be the AND gate? For high output, both A and B, A and B have to be high. Then only you will get high output. Otherwise, the output will become low. It is a logic gate with 2 or more inputs and only one output. The output is high only when all the inputs are high. If all the inputs are high, then the output will become high. Otherwise, it will remain low. So the symbol of the OR gate looks like this. It is like a letter D with 2 inputs, A and B, one output. The output is denoted by Y. Okay. So the logical relation A dot B, and that's what is A and B. A and B. Using the switches, how to realize the AND gate? See, for the current to pass through this circuit to reach this bulb and for the bulb to glow, you need to close both the switches 1 and 2 or A and B. If only one is closed, the circuit will remain open circuit and bulb won't glow. Isn't it? So both are closed means when both are ones, then only you will get high output, that is 1 here. In all other cases, when both are open or when any one is open, the output will remain low. So when both are open means both are zeros, bulb won't glow. A, B are the inputs, Y is the output. Y remains low when both A and B are low. What happens if first switch is closed and the second switch is open? B is open, 0. So 1 and 0. Is the bulb glowing? No. Current is not passing through this. So bulb won't glow. It gives you 0 output. Say first switch is open and second one is closed. This is closed. Even then, no current will pass through this. B becomes 1. 0 and 1 are the inputs. Even then, since current is not passing through this portion of the circuit, bulb won't glow. That gives you 0. If both are closed, A is closed, that means it is made 1. B is also closed, that is made 1. Then bulb will glow, that gives you 1. 1 and 1 will give you output 1. See, for high output, that is 1, both A and B have to be high. If A and B are high, then only output is high. Otherwise, in all other cases, it will remain low. Understood? What is AND gate? AND relation. When A and B are high, the output becomes high. When it comes to the previous gate, when A or B is high, or when both A and B are high, the output will become high. But for AND gate, both need to be high for high output. In all other cases, it remains 0. So this is the truth table of AND gate. Now let us see how to realize this AND gate or how to construct AND gate using diodes. Again, there are 2 diodes D1, D2 for 2 inputs A and B. Output will be taken across this load. Okay. And truth table. When both A and B are high, the output is high. For all other combinations, it remains 0. Okay. Now, for AND operation, the important relations are, see, with A dot 0 is always 0 irrespective of the value of A. A dot 0. A can take up two values, either 0 or 1. 0.0 is 0. It is like multiplication. 1 into 0 is also 0. That's why A dot 0 is always 0. A dot 1, that is A multiplied by 1, is again A. 0 into 1 is 0, or 1 into 1 is 1. You will get back A. A into A, either 0 into 0, that gives you 0, or 1 into 1, that gives you 1. So A into A is A. So remember these relations. That is about AND gate. Understood? Fine. Now, another gate, NOT gate. See, it is a gate with one input and one output. Whatever input you give, either 0 or 1, two inputs, two values are possible for the input, right? If you give 0, that becomes 1. If you give 1, that becomes 0. Such a gate is called NOT gate. The input value gets negated. The input value gets negated. It is a logic gate which has one input and one output. The output of NOT gate is 1 only when the input is 0. And it is vice versa. The output is 0 when the input becomes 1. Okay. Now, coming to the NOT gate, it is simple diode with a negation. This is the NOT gate symbol. NOT gate symbol. Okay. The symbolic representation of NOT gate looks like this. Even an AND gate, this is AND gate, right? This can be negated here. If the two inputs are commonly connected, this will also act as NOT gate. Not only AND gate, even an OR gate with two inputs, if these two inputs are commonly connected and if the output is negated, that also acts as NOT gate. So if you give input as A, here output becomes A negation, A bar. A will become A bar in this case. If A is given, the output Y is A bar. That is NOT gate. So the symbolic representation of NOT gate, a diode with negation, or an OR gate with negation, and even AND gate with negation. Negation is nothing but inverting the input value. 0 becomes 1, 1 becomes 0. That negation is denoted by a small circle associated with that original gate. AND gate with a small circle here becomes a NOT AND gate. If the two inputs are commonly connected, whatever value you give here 0, the same 0 is taken for both the inputs. So it acts as a gate with single input. Then it becomes a NOT gate. Okay. Now, using a switch, the NOT circuit, very easy to understand. See, when current is passing through this battery this way, here are two parallel paths. In one path you have a switch, in another path you have a bulb. See, when switch is in open mode, means when switch is 0, input is 0, the only path available for the current is through the bulb, so that bulb will glow. So you will get output Y as 1. What happens if you close this switch? Once the switch is closed, that means when this input is made 0, all the current will pass through this path, through this switch, low resistance path. No current will pass through this bulb because there is high resistance. So current will be bypassed through this switch and bulb won't glow in this case. So when input is 0, output becomes 0. That's what is NOT operation, right? The input gets inverted, negated. 0 becomes 1, 1 becomes 0. The same can be realized with a transistor here, with a single input, single output. It is a transistor in common emitter configuration. This is emitter, this is base, here is collector. emitter, base, and collector. Common emitter configuration. Coming to the truth table, there is a single input. For single input, only two possibilities, either 0 or 1. When input is 0, output becomes 1. When input is 1, output becomes 0. One input, one output. Now for NOT operation, A plus A bar is its inverted value. A plus A bar is always 1. See, A can take up only two values again, and we have been discussing the same point. Remember it. Only two values are possible for this input. A plus A bar. Suppose if A is 0, 0 plus 0 bar, negation of 0 is 1. That is 1. Suppose if A is 1, negation of 1 is 0. 1 plus 0 is also 1. So that's why A plus A bar is always equal to 1. Okay. Another one, A dot A bar, multiplication here. If A is 0, multiplied by A bar, that is 1. 0 into 1 is 0. If A is 1, dot is nothing but multiplication, remember that. Then its negation is 0. 1 into 0 is also 0. So irrespective of the value of A dot A bar is always 0. A plus A bar is always 1. Okay. And this is an important bit even. This bit appeared in previous entrances. A plus A bar is always equal to 1. A dot A bar is always equal to 0. Now, coming to the combination of gates. As I told you, these OR and AND gates can be combined with the NOT gate to get NOR and NAND gates. So first NOR gate. NOR is nothing but not OR. It's not plus OR. A logic gate which is combination of OR and NOT is called NOR gate. OR and NOT or NOT and OR anyway. So it's an OR gate. This is OR gate and this is NOT gate. This combination is NOR gate. Just opposite to OR gate output. So symbolic representation, this negation NOT gate is given here as negation. Okay. OR gate with a negation becomes NOR gate. Understood? Now, its mathematical operation is for OR gate, Y is A plus B. Now, this output is negated completely. A plus B bar. Y equal to A plus B whole bar. Now, it's a truth table for NOR gate. See, for OR gate, the possible output values I am writing here. For 0, 0, it is 0. For 0, 1, 1. 1, 0, 1 and 1, 1 also 1. This is for OR gate. Now for NOR gate, it is exactly opposite of that output you can take. 0 is inverted, negated, that is 1. These three ones are negated, they become zeros. So 1, 0, 0, 0. These are the outputs of NOR gate. This is NOR. This is NOR. Okay. So OR and NOR. Understood? Next. Another gate, NAND gate, which is not AND. It's not AND. That is NAND. When an AND gate is combined with a NOT gate, the resultant is NAND gate. So this is AND gate and here is NOT gate. Symbolically, it is represented with a negation associated with AND gate. See, AND gate with a negation here, a small circle. That means the output is reversed. Whatever output you are supposed to get for AND gate, that will be reversed. That is NAND. So its mathematical operation is A dot B for AND. Y equal to A dot B. for AND. This is negated, not AND. That's what is NAND. Okay. So it's A and B whole bar. A and B whole bar, or A dot B whole bar. Now see the truth table. On the left side, I'm writing the actual truth table of AND output. AND. When both inputs are low, output is low. When any one input is low, the output is low. When both inputs are high, when A and B are high, the output is high. This is for AND. Now for NAND, it is exactly opposite. 0 becomes 1. This 0 is negated, that is 1. This 0 is also negated 1. And the last one becomes 0. See the difference between AND and NAND. Not AND. That's it. Very simple. And these two gates, NOR gate and NAND gate, are called universal gates. These two are called the universal gates because any other gate can be constructed with the help of these two gates. Using NOR and NAND, you can make AND gate, OR gate, NOT gate. Any gate can be constructed using these gates. That's why these two are known as universal gates. Okay. Now, another gate which is exclusive OR gate. It is exclusive OR gate. Already we have discussed about OR gate and not OR gate. Now it is XOR gate, exclusive OR gate. Now coming to the exclusive OR gate, the symbol looks like this. It is OR gate with additional symbol here. Okay. And its truth table, exclusive OR gate will get high output when the inputs are dissimilar. When the inputs are dissimilar. When both are zeros, it is 0. When both are ones, it is 0. For dissimilar inputs, what are the possible combinations? 0, 1, 1, 0. For these two cases, the output is high. See, for similar inputs, 0, 0, output is 0. Again, for similar inputs, 1 and 1, even then output is low, 0. When inputs are dissimilar, one input is low, another input is high, then you will get high output. One input is high, another input is low, then output is high. For dissimilar inputs, output is high. That's what is exclusive OR gate. XOR gate is also known as exclusive OR gate. Okay. Now, its mathematical operation is y equal to a dot b bar plus a bar dot b. A dot b bar plus a bar dot b. That is the mathematical operation. Then how to construct a circuit to get this mathematical output? See, this is the circuit which gives exactly this output. Two inputs A and B. Now, for the first gate, A is negated. This is A bar and B is directly taken here. It is AND gate. That means A bar dot B is the output here. Coming to the another AND gate, A is directly taken as one input. This is A and B is negated, B bar. It is AND gate. So A dot B bar followed by OR gate. OR is simple addition. That means these two are added. A bar dot B and A dot B bar are added. This is OR operation. The last OR gate performs this action. Okay. So this is exclusive OR gate. A dot B bar plus A bar dot B. That is exclusive OR gate. What if this output is negated? Can you name that gate? Just try it. Becomes exclusive NOR gate. So that's what is XNOR. Exclusive not OR gate. symbol of exclusive NOR gate, same as exclusive OR gate with a negation here, but the output is changed here. When both inputs are similar, the output is high. When both inputs are similar, the output is high. In all other combinations, it is low. Just opposite to XOR gate output. XOR gate output. So exclusive NOR gate it is. XNOR, exclusive NOR. What is its mathematical operation, the Boolean expression for this? A dot B plus A bar dot B bar. Now to get this output, the circuit looks like this. See, first you have AND gate with two inputs A and B. So output is A dot B. And again, these two inputs are negated. This becomes A bar and here it is B bar. AND gate, A bar dot B bar. Followed by OR gate, simple addition. That means A dot B plus A bar dot B bar. That is the Boolean expression for this exclusive NOR gate. Understood? Now, here are certain theorems known as De Morgan theorems, which are very useful to simplify the complicated networks. The first one is A plus B whole bar is equal to A bar dot B bar. Remember, plus represents OR gate. Okay? Dot represents AND gate. So conversion of OR gate into AND gate. When A plus B is OR gate output, it is completely negated. That means it is totally NOR gate output. The same output can be obtained by an AND gate with negated inputs A dot A bar dot B bar. Similarly, what if the operation initially is dot AND? A dot B whole bar, that is A bar plus B bar plus dot is converted to plus. Also, double negation A bar bar. Double negation cancels that negation and you will get back A. Similarly, for B, if it is double negated, that is same as the original input B. A bar bar or double negated A is same as A. Double negated B is same as B. Okay. Next. Making use of these four, what if A bar plus B bar whole bar is there? See, from the first relation, A plus B whole bar is A bar dot B bar. In place of A, we have A bar already. A bar plus B bar whole bar. So from this relation, it must be A, first one negation dot second input negation. First input is A bar, its negation, double bar. Second input is B bar, its negation. So B bar bar. And A bar bar is nothing but A. So this is A dot B. A dot B is nothing but AND output of two inputs A and B. Okay. Similarly, A bar dot B bar whole bar. A bar dot B bar whole bar is A plus B. This is just OR output. OR gate output A plus B. A dot B is AND gate output. Okay. Very interesting, right? At the same time, very easy too. And these concepts are very much important, as in every competitive examination, we see at least one question based on these logic gates, be it a NEET or JEE Main, and sometimes in CUET, and of course for your board examinations, these concepts are very, very important. At the same time, very easy too. Now, let's have a look at some previous JEE, NEET, JEE and NEET questions based on these logic gates. For more such interesting videos, you can subscribe to our channel, Time for IITJEE NEET. Coming to the first question, here is a logic gate given. Combination of gates AND, OR, NOT, NAND, 4 different gates are there. Consider the following logic circuit, and from that circuit the output Y is 0, output must be 0. So this value is decided, it must be 0. For what combination of inputs? See, for the output to become 0, what are the possible combinations? See, for questions like this, it is better to go with the options. Check with the given first option, 1, 0. A is 1, B is 0. If A is 1 and B is 0, this A is directly given here and B is directly given here. 0 and 1 are the inputs for the AND gate. AND gate. So it gives output 0, means this is 0. Now coming to the lower part, see, A is negated. This is A. Here it is A bar. A value is 1. That means it becomes 0. B is directly taken here 0. 0, 0 are the inputs for OR gate. This is also 0. So 0, 0 are the inputs for the NAND gate. For AND gate, 0, 0 gives 0. NAND gate gives 1. But we need to get 0. So first one is not correct. Try the second one. 0, 0. When both are zeros, see, this is 0, 0 input, 0 output. So for NAND gate, first input is 0. Next, coming to the lower part, A is negated. So this becomes 1. B is directly 0. So 0 and 1 are the inputs for OR gate. It gives 1. So 0, 1 are the inputs for the NAND gate. That again gives you 1. But condition is output must be 0. So B is also gone. Now 1 and 1 are the input combination left with, that is option C. Let us check 1 and 1 combination. This is the easiest way in case of logic gates. When both inputs are 1 and 1, this is 1. For AND gate, the two inputs are 1s. So you'll get output 1. Okay. For the OR gate, A is negated, that becomes 0. This is 1. Again, it gives 1. OR gate, if any one input is high, output is high. OR gate gives 1. 1, 1 are the inputs. For 1, 1 input, NAND gate gives 0. That's what is the condition, right? Y has to become 0. That means the right option here is option C. C is the correct option. Very easy, right? There isn't any calculation involved in it. How are the inputs modified with the given gates? That you need to check. That's why this is very easy. And you can get the 4 marks or allotted marks surely for these questions based on logic gates. Moving to the next question. Again, here is a logic circuit. In the digital circuit shown in the figure, for the given inputs are already decided here. 1 and 1 are the inputs. The values of P and Q are actually the outputs. As inputs are known, you don't have to try with the different combinations. Just proceed with these inputs. When 1 and 1 are the inputs for this first gate, what is this first gate? Yes, it is NAND gate. NAND gate gives 0 output. For 2 high inputs, NAND gate gives 0 output. So this input for the AND gate is 0. The same is taken as one input with a negation for the NOR gate here. So 0, here it is 0, other side it becomes 1. Now coming to the lower part, this 1 and 1 both are negated. Here it is 1 and this is 1. After NOT gate it becomes 0 and 0. 0, 0 are the inputs for the OR gate, so it gives 0. The 0 is given as one input for the AND gate. So this is 0. Okay. And this 0 is input for the NOR gate even. Now coming to this AND gate P. When 2 inputs are low, output is low. That means P becomes 0. Once if you know that P is 0, you can rule out option B and D. Either it has to be A or C. Now let us take Q also. So for the NOR gate, inputs are 1 and 0. 1 and 0. For OR gate, it would become 1. NOR means it's a negation. So it gives you 0 here. So Q is 0. P is 0, Q is 0 is here in option C. That means A is wrong. C is the right option for this question. Understood? How to analyze these logic circuits, digital circuits. Sometimes you can use Boolean algebra too. The truth table corresponding to the circuit given below is truth table. A and B are the two inputs. Simple OR gate here and followed by AND gate. C is the output. For A, B inputs, C is the output. You can try with the different values. Only 4 combinations are possible here. When both are zeros, one input for AND gate is 0. Output also gives 0. 0, 0 are the inputs for the AND gate. Output would become 0. For 0, 0 combination, output is 0. Say, based on that, you can rule out option B and also C. Because 0, 0 inputs are getting output 1 in this case. Here also it is given as 1. That's why these two can be ruled out. Now it has to be either A or D. Now, which combination is different? You don't have to check with 1, 1, 1. In both 1, 1, 1 is same. 1, 0 is 1, 1, 0 is 0 here. Let us check this combination to identify the correct option. So take the input combination A 1, B 0. A is 1, B is 0. If A is 1, that A is directly given here, so it becomes 1. When A and B are the inputs for the OR gate, if any one is high, the output becomes high. So high output is given here. That acts as input for the AND gate. When both are ones, both are high, the output is high. So 1, 0 combination gives 1. 1, 0 combination is 1 here, whereas 1, 0 combination is 0. So this is not correct. So right option is option A. Okay. Very easy question. And this appeared in recent JEE mail. Another question. The truth table for the circuit given below is, what is the output? See, first A is directly used here, but B is negated and AND gate. It is A dot B with negation B bar. See, second gate, B is directly given to the input and A is negated. That means A bar dot B, because it is AND gate dot. Now these two inputs are fed to the OR gate. OR gate is simply addition. So your Y is A dot B bar plus A bar dot B. Now do you remember this combination? A dot B bar plus A bar dot B. This is nothing but the output of exclusive OR gate, right? XOR gate. So for XOR gate, output is high when inputs are dissimilar. In all other cases, it is 0. So for 0, 0 input, output is 0. We have nothing to do with that because in all options A, B, C, D, 0, 0 is giving 0. But 1, 1 will also give 0 for exclusive OR. So based on that, you can rule out option A. Yes. Now for dissimilar inputs, the output has to be high. When 0 and 1 are the inputs here, 0 and 1 are the inputs, output is not high. Output is shown low. So this is wrong. Again, when dissimilar inputs are given, output is low. This is also wrong. When dissimilar inputs 0 and 1 are given, output is high. 1 and 0 are given, output is high. In all other cases, it is 0. So this is the exclusive OR gate output. So correct truth table here is D. Option D. Understood? So even this is an XOR gate. Exclusive OR gate it is. Let us see another question. A question with two NAND gates and one NOR gate. For the circuit shown above, equivalent gate is it NOT gate, NAND gate, AND gate, OR gate? Let us check with the possible combinations of the inputs. Let's take up a truth table here. A, B, and Y. First, let us try with 0 and 0. If 0 and 0 are given as inputs, for 0, 0 input, NAND gate gives 1. And also 0, 0 inputs, NOR gate gives 1. 1 and 1 are the inputs for the NAND gate. So it gives 0. So 0, 0 gives 0. Okay. So if it is 0, 0, 0 combination, it cannot be a NOT gate. It cannot be a NAND gate. Because if you check the truth table of NAND gate, for 0, 0 combination, you get output 1. But here output is 0. So you can rule out these two. Now is it AND or OR? Let us try with another combination which decides the answer, which is 0 and 1 combination. If it is not, if it is AND gate, you get 0. If it is OR gate, you will get 1 here. Let us check that one. So erasing all this. Now the inputs are 0 and 1. When 0 and 1 are given as inputs for the NAND gate, that gives you 1. Isn't it? For AND gate it is 0, NAND gate it is 1. So that 1 acts as input for the second NAND gate. Again, for this NOR gate, A is here, that is 0, and B is here, that is 1. 0 and 1 are the inputs for the NOR gate. OR gate would have given 1, but NOR gate gives 0. So that acts as the second input for the NAND gate. 0 and 1 or 1 and 0 are the inputs for the NAND gate. For AND gate, output is 0. For NAND gate, output is 1. 0, 1 gives 1. See, if any one input is high, the output is high. That means it's only OR gate. It cannot be AND gate. So right option is option D. You don't have to check with all the 4 combinations. 0, 0 is giving 0, 0, 1 is giving 1. Similarly, 1 and 0 combination will also give you 1. 1 and 1 will give you 1. This is same for OR gate and AND gate. That's why I'm not checking this one. Okay. This is also same for OR gate and AND gate. The difference comes only in this combination. That's why I tried this one. Understood my logic? Yes. Next one. The output of the circuit is low for. So output has to be low. This output is 0. That is decided. For which combination of inputs it can become 0. See, let us try with the first one. 0, 0 are the inputs. If 0 and 0 are given for the first gate is OR gate. It gives 0. Then you have a NOT gate. NOT gate makes it negated. 0 is negated means that becomes 1, but not 0. So A is not giving low output. This first option, A is not giving low output. So wherever A is there, that can be ruled out. It's not ABC, not ACD, not ABD. Finished. You're left with only one. That is C. So the right option here is C. Except the first combination 0, 0. For all the remaining 3 combinations, you will get output as 0 here. That's why B, C, and D only. For all the 3 combinations, you'll get low output. Understood? Yes. The output Y of following circuit is given for given inputs is when A and B are the inputs, what will be the output? Let us check that. See, first is OR gate, second is AND gate, and last is also AND gate. For OR gate, what are the inputs? A is directly taken and B is negated. OR gate. So A plus B bar it is. Lower side, you have AND gate with A negated. A bar dot B. Okay. And finally, these two are the inputs for the last AND gate. So what is Y? AND it is A plus B bar. A plus B bar. AND means dot operation. Another one is A bar dot B, second input. Okay. Now, if you open this bracket, it is A dot A bar dot B plus multiplying with B bar again. B bar dot A bar dot B. So here A is multiplied with these two first, then B bar is multiplied with these two first with plus sign in between. Okay, right. So what is A dot A bar? If you don't remember, you go back and see. A dot A bar is 0. Similarly, B dot B bar, this will also give you 0. So 0 dot B is again 0 plus 0 dot A bar is 0. So finally becomes 0. That means right option is option D. D is the right option for this question. Okay. So writing these Boolean expressions also, you can solve these questions instead of using combinations 0, 0, 0, 1, 1, 0, 1, 1 like that. You can use these Boolean expressions also to simplify these networks. Okay, right. Now, for any classroom coaching inquiry, you can visit the nearest time center, or you can visit our website for more details about our courses. That is www.timeforeducation.com. Now, let's have a look at some NEET questions based on these concepts. Here is the first question appeared in recent NEET entrance. The output Y of the given logic implementation is similar to the output of a gate or AND gate or NAND and NOR. So this output is similar to output of which gate? See, A, B, only two inputs are there. Okay. Let us try with 0, 0. When 0 and 0, A is 0 means here also it is 0. When 0, 0 are the inputs for the NOR gate, it gives one output. Similarly, NAND gate also gives one output. Output becomes 1 here. So 0, 0 combination is giving 1. A is 0, B is 0, output Y is 1. Now, let's try with 0, 1 combination. 0 and B is 1. When 0 and 1 are the inputs for the NOR gate, that becomes 0. Yes. And similarly for the lower gate, 0 and 1 are the inputs for the NAND gate, that gives you 1. So 0, 1 are the inputs for the last AND gate. AND gate gives you 0. So 0, 1 it is 0. Next, change the combination. A is 1, B is 0. A is 1, B is 0. So when 1 and 0 are the inputs for the NOR gate, output is 0. When 0 and 1 are the inputs for the NAND gate, output is 1. For these two inputs, AND output is 0. So 1, 0 becomes 0. What if both are ones? Both are ones. A is 1, B is also 1. For 1, 1, NOR gate output is 0. For 1, 1, NAND gate output is 0. For 0, 0 inputs, output is 0 for the last AND gate. So this is the final output. Now this is the truth table of which gate? It is just opposite to OR gate. That means this is NOR gate. So NOR is here option D. Understood? Yes. Let us see another question. When the output of an OR gate is applied to input to a NOT gate, then the combination acts as OR gate. This is an OR gate. Okay, with the two inputs. The output is given as input for the NOT gate. Then OR and NOT combination it is. Nothing but NOR. Okay. So NOR is here in option B. Understood? Next one. The output Y for the inputs A and B of the given logic circuit is. What is the output for the given inputs? See, this is like a NOT gate. This is also like a NOT gate because the two inputs are commonly connected. When A is used here, it becomes A bar here. When B is used here, it becomes B bar here. A bar and B bar are the inputs for the NAND gate. NAND gate. NAND gate means complete negation of the inputs. So Y is the inputs are A bar and B bar. AND operation is dot. NAND operation is its negation. Okay. Now from De Morgan's theorems, what is A dot B whole bar? It's A bar plus B bar. Then A bar dot B bar whole bar, nothing but A plus B, no? So output is A plus B. You can directly mark it as C. See how it is simplified. Okay. Next. Another question. The output Y of the given logic gate is similar to the output of which of these gates? The output of this logic gate is similar to which of these gates? See, it is again combination of two NOT gates. This is NOT gate, this is also NOT gate. Yes? So for A input, here output is A bar. For B input, output is B bar. That is fed to NOR gate. NOR gate is addition, isn't it? So Y is A bar plus B bar. This is OR, NOR. NOR. So complete negation. What is A bar plus B bar whole bar? From De Morgan's theorems once again, it is A dot B. So A dot B means dot operation is meant for AND. So output Y here is similar to the AND gate output. So you need to mark your answer as C. Hope you're following. Right. So then the question, for the following logic circuit, the truth table is, what is the correct truth table for this logic circuit given here? Again, two NOT gates are used. A is negated, so input here is A bar. B is negated, input is B bar. That is fed to NAND gate. So NAND gate, just now we have discussed. Y is A bar dot B bar NAND. Complete negation. What is A bar dot B bar whole bar? It's A plus B. A plus B means OR gate. Right? Now check the truth table of OR gate. OR gate truth table 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. This is correct. 0, 1, 1. This is correct. 1, 0, 1. This is correct. 1, 1, 1. So this is OR truth table. That means the right answer is option A. Understood? How to handle these questions based on logic gates. In fact, they are very simple and easy, easier than questions from any other chapter in physics. That I can say confidently. Okay. So, hope you have enjoyed this session. If you have any confusion, go through the video once again. You will get complete clarity on these logic gates. Thank you very much for watching. See you in the next session. Take care. Bye.